Here's the magnet servo motor in slow motion. First at 1/4 speed and then at 1/8 speed. The reason I did this is to analyze or at least observe the working of the motor. You can see the red end of the motor, which is the north pole of the magnet, and the red wire and the blue wire and the green wire. So you can see the red end of the magnet turns by the servo between the blue wire and the red wire. So it goes back and forth. It doesn't quite go 180 degrees, it's more like 140 degrees. Now, the motor works, the motor has a stator, it has two magnets taped to the side of that hoop on each side, just like a DC motor, and the servo reverses the position of the magnet on the armature, and the magnet being attracted and repelled by the stator makes the motor turn, the armature turn. So, it's made of 5 1/2 inch diameter N42 neomagnets on the armature. And it has two light-dependent resistors, LDRs, an Arduino microcontroller, and a 9-volt battery powering the servo. Rationally, I'm not promoting the motor as energy coming out of thin air. But there is something fascinating about this motor. So after giving it some thought, I noted that the servo turns at the same speed as the motor. So you'll see the servo going from the red wire and turning clockwise to the blue wire, then turning counterclockwise back to the red wire. So the magnets, well, when you see the servo turning clockwise, you'll notice that it stays in the same position relative to the frame of reference. So the magnets weigh less than the motor armature. The motor armature weighs about 4.5 ounces, and the magnets only weigh about 1 ounce. The servo is stopped at certain times where the gears lock it into place. When the servo is not turning, the servo turns and then stops and waits for the motor to catch up, with the magnets to pull the motor or the flywheel effect to turn the motor around. So it all should somehow be accounted for as far as where the forces and torques and energies are coming from. So I'm thinking it takes the same energy to turn the servo magnets against the stator as is gained by, that's the loss or the electricity used by the servo, and it takes just the same amount of energy that the magnets pull the servo around, the magnets pull the rotor around, or the magnets pull the armature around with the stators, or forced by the stators. Consider this, however, there's something called slip. So say magnets repel as they approach, they will go right past without stopping. This is sort of like a propeller in water on a boat. It can only go so fast, past a certain speed. It's not going to make any more thrust because the water just gets out of the way. Also, like magnetic gears, slip is a strong point that they emphasize when they sell magnetic gears because it prevents damage, whereas mechanical gears would jam. So the slip is like, it's like when you slip on ice. there's no energy lost. It's kind of like if you push against the wall and the wall doesn't move, there's no work done, but you really did push. You're using up something, energy, I don't know what you would call it. It's not force really, because force is mass times acceleration, and there is no acceleration. There's just your hand standing still, the wall standing still, but you're applying pressure to your hand. So it's sort of like that. And also consider that magnets moving towards each other or from each other don't become stronger or weaker. So if you have an experiment where you have two magnets and the repelling ends are together, the like ends are together, and you move them towards each other and suddenly stop, there's no more force that you can measure than if they were already positioned there still in that position. But not to get too sidetracked, back to magnetic propulsion. The armature isn't perfectly balanced. So the heavier part gets some momentum, causing it to gain sort of an orbit, to go in sort of an orbit. But when it turns clockwise, when the motor turns clockwise, the motor is seen turning counterclockwise in this video. But when the motor turns clockwise, the timing is out of phase a little bit from time to time, and it swings more to one side. This is because the heavier part of the armature is in one position when it's in phase, whereas it's accelerating, and it's in another position when it's out of phase, whereas it's decelerating. And its momentum tends to push in a line, in a linear motion. So that's about all I have for today. So please like, subscribe, give me a rumble, and thanks for watching.